All right, let's dive in. Today, we're going to pull back the curtain on one of the most useful skills out there, thinking like a programmer. We're going to break down the thought process that turns a big, messy problem into a clean, working program. And you might be surprised to find out that the actual coding part is a lot smaller than you think. I mean, really think about that for a second. You've got a system managing thousands of trains, millions of seats, and who knows how many people, all trying to book tickets at the exact same moment. How in the world does a machine handle that? It seems impossible, right? Like some kind of magic? But the secret isn't what you'd expect.
And there it is. That's the big secret. Computers, at their core, don't actually solve problems. Not really. They are just incredibly fast, incredibly obedient little machines that follow instructions. The real brainpower, the real genius, isn't in the hardware. It's in the recipe. The plan we create for them. And that plan, well, it always starts in the same place.
With a problem. This is ground zero. It's the most important step of all. Before you can even dream of writing a single line of code, you have to truly, deeply understand what it is you're trying to accomplish. You can't write a perfect recipe if you don't even know what you're trying to cook, right?
So this whole journey, from a simple idea to a finished piece of software, can pretty much be broken down into these 4 key steps. First, you analyze the heck out of the problem. Then, you design the recipe, or what we call an algorithm. Only then do you actually sit down and code the program. And finally, you test it and fix all the bugs. See? Coding is just one part of a much bigger process. So let's zoom in on that second step, because honestly, this is the real heart of programming, the algorithm. This is the blueprint for our solution. It's the game plan we map out long before we start building anything.
So what in the world is an algorithm? Well, the official definition tells us everything we need to know. It's a finite sequence, which just means it has to end at some point. And it's made of precise, step-by-step instructions. There's no room for guessing. You just follow the steps and you get the result. It's that simple, but it's also that powerful.
The recipe analogy is absolutely perfect here. If a recipe says add a pinch of salt, that's a terrible instruction for a computer. What's a pinch? My pinch is different than your pinch. A computer would get stuck. An algorithm has to say add exactly 1.2 grams of salt. It needs to be totally precise. And every good algorithm has to play by a few basic rules. It has to be precise. No vague instructions. It needs a clear stopping point. No getting stuck in an infinite loop. And, it has to actually do something. It takes some input, like the ingredients for a cake, and it produces a reliable output, which is the finished cake.
Okay, so you've thought through the problem, you've got this brilliant plan in your head, but now what? How do you get that plan out of your brain and onto paper before you start wrestling with actual code? You need a way to see the logic.
Coders usually have 2 main tools for this. On one hand, you have the flowchart. It's totally visual, a blueprint made of shapes and arrows that shows you exactly how the logic flows. And on the other hand, you have pseudocode. It's kind of like a simplified version of English mixed with code, focusing only on the steps without worrying about the strict grammar of a real programming language. Let's look at a super simple task, finding the square of a number. See how they line up perfectly? The input num box in the flowchart matches the input num command in the pseudocode. The process rectangle becomes the compute line. They're just 2 different languages telling the exact same logical story.
But very few stories and very few algorithms are just a straight line from beginning to end. Just like in real life, you have to make decisions or do things over and over again. In the world of programming, we call this controlling the flow.
And really, there are only 3 fundamental ways to direct the logic. Sequence is the default, just doing one thing after another. Then you've got selection, which is basically a fork in the road. If this happens, do that, else do something different. And finally, repetition, which is just repeating a bunch of steps over and over in what we call a loop. This is a perfect example that has nothing to do with a computer. The lamp isn't working. That diamond shape in the flowchart is asking a question. Is the lamp plugged in? That's a selection point. Your answer yes or no sends you down a totally different path. And that is exactly how a computer program makes decisions, just with data instead of light bulbs.
So you've designed your algorithm. You're done, right? Not so fast. A first draft is almost never the final draft. Now comes the really critical phase. You have to test and refine your logic to make sure it's not just kind of right, but that it's actually correct and as efficient as possible.
So let's look at this little algorithm for adding 2 time values. You input 2 sets of hours and minutes. You add the hours, you add the minutes,
and then you print the result. Seems totally logical, doesn't it? What could possibly go wrong?
Ah, but here's the catch. We've run a little test. What happens when the minutes add up to more than 60? Our algorithm spits out 6 hours and 70 minutes. And while that's technically correct math, it's not how we tell time. We've just found a flaw in our logic, and that's exactly why we have to test our assumptions.
So we go back and we refine it. We add a selection step, that if-then logic. Now, if the total minutes are 60 or more, we add 1 to the hour and then subtract 60 from the minutes. We've added a rule to handle that overflow, and just like that, our algorithm gives the correct answer, 7 hours and 10 minutes.
But here's the next level of thinking. Getting the right answer is only half the battle. For almost any problem you can imagine, there are multiple correct algorithms. The real challenge is to find the most efficient one, the one that gets the job done the fastest with the least amount of work.
Take finding a prime number. Method 1 is to check every single number below it. Sure, it works, but it is painfully slow. A slightly smarter method only checks numbers up to half the value. But the most efficient of these three only checks up to the number's square root. All three algorithms are correct, but that third one is just orders of magnitude faster.
And all of this really brings us back to the core philosophy here. You take a big, intimidating problem, like that railway system, and you decompose it. You break it down into smaller, simpler problems that you can actually solve, like how do I book one seat, or how do I check one train schedule? You get your thinking straight on those simple problems, and then you put them all together with, as the quote says, logical glue.
So that's the blueprint. It's not about being a math wizard or knowing some secret computer language. It's a structured way of thinking, of breaking down problems and building logical, step-by-step solutions. It's a superpower you can apply to just about anything. So the only question left is, what problem are you going to solve?